Let us look at this problem. They're asking us to draw the shear and bending diagram, the moment diagram, and determine the maximum value of the bending moment. So first of all, notice that they have given us a beam with points A and D, which have supports. A has a fixed force with forces A, Y, A, X. Right now we can see that there's no other force because at D we have only a roller, and a roller does not have forces in X. Therefore, we know that this one is 0. They're also giving us a point B and a point C, where we need to, that's going to help us determine the points, the shear forces for the diagram. So since they're asking you to draw a diagram, you basically have to look at the system and see where there are changes. At those changes, you basically use those points to draw the curves. So if we go ahead and try to find our forces, we'll see that we have some distributed load W, and the area or the region where the load is applied is called A. So summation of forces in Y equals 0. You're going to take positive going up. So we have AY plus DY minus the distributed load. We know how to do this part is W times the region where it's applied. Since this is a uniform rectangular load, it's just simply base times height. W's height, base is A. If it's not regular, then we'll have to do some other computation and just find the shape of the load. If it's a triangle, if it's parabola, anything else. But we have those, two of those. So we have to do this number equal to 0, negative W times A, 2 times that. So basically this means that AY plus dy is equal to 2 times the distributed load. All right, so we have, well, this W is known, A is known. Here is just a parameter for, just to keep a concept, but those things are known. What is unknown is A and D. So we have one equation, two unknowns. We need another equation. So let's do equation number 2, summation of moment at A equal to 0. So for that, should be pretty simple. Let's start with D. dy times L, that is a positive moment because it's going counterclockwise. Then we have WA, the first load close to A. We have to place that load near as a point load, and it's going to be at A over 2. Remember, we saw this already. So there's a load at this whole distributed load could be conceptualized as a single distributed load, and that's what we'll do now. But this one is clockwise, so negative the load W times A at the distance, which is A over 2. And there's one more, which is also W times A, but this distance right here is going to be L minus A over 2. So minus, because it's clockwise that moment, W times A times L minus A over 2, and this is equal to 0. Okay, so in that case, what we need to do is solve for dy. So let's do this. dy times L is equal to WA squared over 2 plus WAL. This is plus. This is, am I getting confused? I don't want to confuse anybody. So before we do this, let's do one thing. Let's solve this and then change the sign. So negative WA squared over 2 minus WAL plus WA squared over 2 equal to 0. There you go. So that is going with that. Cancel out. Minus, minus, plus. Yep. So now we can do dy times L is equal to, this one to the other side, positive W times A times L. This should be a known value because we know the load, we know the region A, we know the length. All right, and L goes with L, so dy is equal to WA. All right, that makes a lot of sense. This one is the force at the roller. Therefore, if we notice, AY is equal to 2WA minus dy minus WA. This is equal to WA. All right, so AY is also equal to W times A. Okay, perfect. So all this distributed load is W times A, so this reaction is W times A. So if you were to plot the shear force, we need to find it first. But you can picture how right now this is starting to deform like so, right? No deformation here, further deformation here, and then go up. This is deformation. This is displacement. They're not asking for displacement, but I want you to start picturing how this beam is deforming. If it was just like exaggerating straight line here, and deforming and then going back up to the roller. Okay, so with that concept, we can start finding our forces. So let's do a cut at B. So they're telling us that B is around A, right? So this is how you conceptualize B. It's very close to A. So we actually need to use the distance A and a variable x to find the shear moment, and sorry, the shear force and the bending moment at B. So let's do that. So for AC, or section A to C. So we have our beam. There's no forces in X, there's only one force in A, which is AY, and then we have the distributed force. And that force, distributed force, remember, is W, and this region right here is A. Okay, so where the point B was located, because remember, B could be anywhere from where the load is to the next change in loading. So it's anywhere that the point B is anywhere within that region. So we can just know one point and then plot that value on the graph. So you'll see that in a second. right now, let's just go ahead and say that this distance from where we have point A to point B, this is going to be x. And obviously this is going to be point capital A, and this distance is lowercase a. All right, so we have to find V. We already have AY. So for that, let's do summation of forces in y equals 0. Going up is positive again. So we have AY, which we know, minus W times A is just forces, no moments. So here it's just the distributed force, the weight, or the magnitude times the region or the area, minus the unknown, because W is known, A is known. Again, they're just giving us W and A in terms of letters, of parameters, but they're loads that you can know. And in real world, the way you know those forces are with little instrument called strain gauge. We should actually have a little information about a strain gauge because they are used to know how much um, element is deformed, and then you can derive, or you can compute the force based on that deformation. So that's why I'll constantly ask you to conceptualize the deformation. All right, but we have here a force V, and this is equal to 0. Everything here is known but V, so we should be able to find V. So in that case, we have that V is AY, which is WA minus WA. Well, I have something here to fix. So actually, we need to know what is the shear under any arbitrary load. Okay, so A, if we do it at away from A 0, we just did that. We need to do within B, so we know V within this section. Because if you notice, at this point we had that V was going to be AY minus WA, and AY is WA, so V was 0. And that makes sense because after the distributed force, at this point we just found out that V, the shear force, is 0. We care about where the shear force is not 0, V as vector. And that point has to be within the value of capital B, B as Bravo. Okay, so what we have to do now then is compute V as vector within the distance x. In this case, what we need to do is do summation of forces in y equals to 0, and then we have AY minus V, which is the unknown, minus the force, the load W, but then the region, the area of the force distribution now is going to be a random, or not a random, but a variable x. It's anywhere on the x-axis between A and B, obviously. So let's say x bar, and x bar exists between A and B. Okay, now so we can find V, AY minus V. Well, we have the value for AY, so let's do that. So V is equal to W A minus Wx. All right, that makes a lot of sense because V, the shear force, is going to be the whole distributed load from V, from A, capital A, to the point where the distance A is, minus wherever we decide to study, minus the load times X. So when A equals X, it's going to be 0, there's no more load. But when X is smaller, is lower than A, is smaller than A, then we do have a force, which is the whole distributed force minus Wx. Okay, this makes sense. Okay. All right, and they're asking us for the moment here. So don't forget, there's a moment as well. We take positive on the first cut. Okay, so actually this is pretty simple because remember the concept of moment is the integral from L0 to L1 of a force times the differential of the line of the region. Okay, in this case the L is really X. So the moment is going to be really what we have to do is integrate the moment as a function of x is equal to the integral from 0 to x bar of the shear force, which is a function of x, dx. So we saw this concept already. The moment is the integral of the shear of the force times the perpendicular distance or times the line integral. In this case, is the perpendicular distance is pretty simple. So m, the moment, is equal to integral from 0 to say x of xb of wa dx minus 0 to xb wx dx, and this is equal to wax from 0 to xb minus wx squared over 2 from 0 to xb. All right, so this is the moment in x. Let's go ahead and use our values of xb minus 0, so w a xb minus w xb squared over 2, where the distance from A to B is determined by the distance x b. All right, so that was how a simple way of finding the moment from the shear force. And obviously now we can find the moment with integration because we have a function as the shear force, but most times you just have a number, 110 newtons or 2000 newtons, so you don't really get to integrate to find the moment. But this is a good reminder that you can find the moment of a shear force with integration if you know the function. All right, so this is the moment. All right, so let's see, let's plot the first part of the curve. So let's plot it right here. So we have A, B, C, and D. Okay, so we have this and that. One for V, shear, one for moment. We have this and we have that. Okay, we have point A point A, we have point B, we have point C, and we have point D. All right, these values 0 and this value is 0. This is in whatever units we have, newtons or pounds. This is whatever newtons meter we have, or pound force feet, whatever units they give you. All right, so let's start with a shear from A to B. We have that the value of AB, or AY, sorry, is WA. So WA right here. So whatever that value is, WA. And if we do a point away from B after the load, we actually did that part too. We have that AY minus the whole load, WA, minus V equals to 0. This is V after the point B, D as Bravo. So the shear after the distributed load. This force right here is before the distributed load is ending. This point is after the distributed load is ending. So AY is WA, so this point is 0. Okay, therefore we know that at this point we have 0 from B to C, and that is basically because there's no, as we said before, there's no force from B to C. But from A to B, we found that we have WA minus WX. This is W times A minus X. So this is a negative parabola, sorry, a negative straight line. And at crossing A, so A minus X is basically this line right here. All right, so if you remember where we found V, we said by theory that you can find the moment by integrating. The integral of a straight line is a curve, so we know that the moment is a curve. Let's go ahead and find that. So wherever x is 0, we're going to have 0 minus 0. We're going to have our moment is going to start at 0. And wherever we have a, we're going to have WA squared. So we're, if x equals a, we're going to have WA squared minus WA squared over 2. This is W1 minus 1/2 is 1/2 WA squared over 2. So we're going to have a point at which is going to be WA squared over 2. And is going to be a positive, no, it's not going to be a positive. It's going to be a parabola where, well, it's either this way or this way, which concave or convex shape it would be. So at this point we can actually use Wolfram alpha or a plotting tool to let us know what value would be. So if it's a positive parabola, it would be like so at 0, but it's a negative parabola. Oh, okay, that answers the question. So it's a negative parabola. But yeah, if you want, you can use Wolfram alpha to find what this is. Just give this any number, 2 times 3x minus 2x squared divided by 2 and find the shape. But we saw now that it's a parabola going this way. Then at this point, v is 0, meaning that the integral of 0 is a constant. So we have a constant moment. All right, and then we're caught up. Now we have to find the value from C to D. Okay, so let's do that right here. From C to D, in element C to D, let's take those points and try and plot what we have. So we have a section that is going from point C to point D. Right here we have a force, which is dy equals the distributed load. Then we have, let me see something. Their question is determine the maximum. Oh, they're actually not asking us. Well, yeah, we have to find that value right there. So this point right here is the force. This is W, and this is going to be value of X. So at this whole distance right here, remember, is L. But this distance here is X, and actually we don't need to go to L, sorry. It's from C to D, not from A to D. So this is A. So the summation of forces in Y equals 0. So we have D minus W times, same thing, A minus X. So D is equal to, well, of course, minus V equals to 0. It's equal to, actually we wanna find V. So V is equal to D minus WA minus WX. And this is, D is WA. We found that already. So it's basically a negative slope up until we find D, which is WA, going up. All right. So in this case, we have that this is negative. So the moment is going to be the integral of this, which is negative WX squared over 2. Okay. In that case, we have, this is symmetrical, but we have that graph. Okay, at this point we should have known that we just need to close the graph, but we wanted to, for completeness, we wanted to find the other point as well. All right, so now we're ready to find the maximum, and the maximum is pretty simple. The maximum we already found, which is 1/2 of the weight times the length divided by 2. So for point B is 1/2 of WA squared.